All right, how's it going, everybody? We are here for the second part of week one here. We're going to look at section 5.5 today. This is going to cover the substitution rule. I do want to point out there's nobody that calls this the substitution rule. This is very, very commonly referred to this technique as U sub or U substitution. The U in U sub just comes from the typical variable that is used. The technique today is going to be about swapping out some variables for some variables that are going to be more easy for our integration to happen here. And it is for no reason at all, typical that U is the variable that is used in this substitution that we're going to make here. So today we're going to talk U sub. And what we kind of want to think about for ourselves here is what we're trying to do in this class broadly. One of the biggest, probably the single biggest theme of this class is build our integration toolkit, right? We want to be able to integrate as many scenarios as possible. In general, integration is really hard. In general, most integrals can't be done, and the ones that can be done are often pretty difficult. So what we kind of want to work with here is kind of understanding that integration is essentially the inverse of a derivative. We want to see, can we undo lots of the derivative situations that we have previously encountered in Calc 1? What you know in Calc 1 is that you spent a whole chapter in Calc 1 developing derivative rules, right? We got the product rule, we got the quotient rule, we got the chain rule, we got logarithmic differentiation, all this good stuff, implicit differentiation. All of these things are things that we want to be able to undo by way of an integral process, but it is not going to be just quite as easy going backwards as it was going forwards. For example, things like the product rule, we won't really learn a technique for how to undo that until you guys take differential equations, Math 55, one of the next classes that follows this one. After you take Calc 2, that is the prerequisite for both Calc 3 as well as differential equations. Both those classes are amazing. I very highly recommend both. I'm teaching differential equations this semester. It's awesome. But again, kind of what I'm saying is even the product rule, a relatively simple derivative rule, isn't something that we learn how to undo even until one further class beyond this one. It's kind of complicated. Quotient rule, everybody hates the quotient rule. We're not going to work to undo that one. But the chain rule, I hope that all of us kind of took away from differential calculus, calculus 1, calculus of derivatives, that the chain rule is kind of one of the most broadly applicable rules in calculus for derivatives because so many functions are not simple functions, they are compositions of functions. And so the chain rule crops up all over the place, as we know. If you can see the examples at the bottom of my screen, hopefully these look like some derivatives that you don't think you'd have too big of a problem with. What we want to do today is identify when does it seem like the integral that we're attempting to compute may have perhaps come from a derivative associated with the chain rule, right? Can we identify the pieces of the integrand as chain rule components so that we can perform the integration by undoing a chain rule? That's essentially the big concept behind our U substitution today. So because the chain rule is probably the most important derivative rule, it's very important to us as far as integral rules go that we would like to be able to undo that. So let's go ahead and take a look at this. And I think the best thing to always start with here is to say, let's make sure we remember the derivatives that we're taking here so that we understand what it looks like to attempt to undo those derivatives. So just a couple basic chain rule applications here. I'm positive that you guys all remember how to do these ones here. Taking the derivative with respect to x of sine of 3x. I can see here, if I want to think about this sort of in the complicated way here, which I think is overkill in this scenario here, I can think about my outside function and my inside function. Here, my outside function is the sine of x. The inside function, which we have composed with sine x, is the function 3x multiplied by 3. To perform this derivative, we know that we want to take the derivative of the outside function, sine, leaving the inside function left alone. So the derivative of sine is cosine. And we want to leave the inside function alone. Then we multiply by the derivative of the inside function. And we would probably more typically write this as 3 cosine 3x right there. Right? So pretty easy derivative right there. All that we did was popped out a constant of 3 when performing the chain rule derivative right there. Nothing too crazy. Other one over here, the derivative of e to the x cubed plus x. Again, here my outside function is the exponentiation, e to the power of. My inside function here is the x cubed plus x. So very, very similarly here, I'll take the derivative of the outside function, the exponentiation. I know that the derivative of e to the x is just e to the x. We're going to leave our inside components left alone. So remember that the derivative of any e stuff is always the entire e expression back again times some other stuff. What is this times? Well, it's times the derivative of that inside function, in this case the x cubed plus x, so that should give us times 3x squared plus 1 right there. All right. So our chain rule derivatives, remember that we've got sort of this outside function and this inside function. What our goal is going to be for integration is that we are going to say some integrals. We're going to see expressions that look like the ones that I've written here. And what we want to be able to recognize, the important thing to see here is that in this expression, right, there's lots of parts to this expression, but within this expression, I can see some terms, x cubed plus x, where I can see both a function, right? I'm saying x cubed plus x is the function, as well as the derivative of the function. Both of those components are contained in the overall expression. So anytime we're attempting to integrate some integrand, where we can see both some algebraic expression as well as that algebraic expression's derivative, that's a good indication to us that we should be using u substitution to help perform that integration right there. And by the way, just to be slightly more technical in what I just said where we see a function and its derivative. Well, it's pretty important that we're doing multiplication in these scenarios right here. We know that like addition isn't something that crops up naturally out of the chain rule, stuff like that. So certainly the mathematical operation also matters, but we're really just looking for like our vague hints towards u sub. If you see a math expression and its derivative, good hint to you that u sub might be the route to go on that guy. So our goal when undoing this differentiation is to identify where we see an expression and its derivative. Since those are the two parts of the chain rule, let's just real briefly recall the chain rule definition here in terms of function notation. Right? The derivative of f of g of x of a composition of functions is the derivative of the outside function with the inside parts left alone, right? G of x was left alone, but we took the derivative of f and then stuck g back inside of it, times the derivative of the outside function. So what we're looking for is we want to go the other direction with this, right? What we want to do is see that sometimes we have integrals that look like this right-hand side, and we would like to integrate these right-hand sides to get back this expression over here on the left-hand side. We're undoing a differentiation here. So let's look at a couple, and I'm going to put these in quotes right now. Easy examples right here. I'll refer to things as being easier and harder this semester. I certainly don't ever mean any offense to anybody. There's plenty of things in math that are hard for people at first and get easier later. I do want to be able to kind of say to you guys when we're working through examples, here's some of the quick ones. Here's the ones that are particularly difficult. So when I kind of put things in a sort of difficulty ranking out there, that is never a judgment passing. That is always just a personal ranking of, in a sense, how I think you should view them once you're comfortable with the topic. So, as indicated a moment ago, what we're hunting for when we're looking at these integrals is scenarios where we see both an expression and the derivative of that expression contained within the integrand, right? When I look at 3x squared times sine of x cubed, I don't just naturally know some antiderivative for that, right? If this was like the integral of cosine dx, then I would just say, well, that's sine and we're done. I just know that antiderivative. This isn't an antiderivative that I know, so now I've got to start thinking to myself, and this is sort of a new train of thought for us since we haven't built any integration techniques yet, but now what we're going to start doing is saying, okay, on my list of techniques that I have available to me beyond just undo a derivative, what do we got right here, right? If I just don't know the antiderivative, this is going to be our very first technique. We're going to get several techniques this semester to help us out with scenarios where we don't just know an antiderivative. So what I'm thinking is that I think that in this one, the reason I'm putting this under the category of easy examples right here is because I think that even if you're not down with U sub yet, that everybody can see that we easily have an expression and its derivative contained and related by multiplication within the integrand right here, right? So this does seem to me to be a very perfect candidate here for u substitution. Now, what we can't do though, or what we should not do, is just like look at this thing really carefully and be like, so what is it, right? What we want to do is have a little bit more of a methodical process here to make sure that we can keep track of all of our components, as you guys are going to see, and hopefully as you believe when I say that these are the easy examples, there's going to be some harder ones later where we can't just necessarily do the mental math here, all right? So what we want to do is perform a change of variable. What I want to do is get this integral out of an x expression and into a different variable expression where the integral will be simpler for me to compute. The way that we're going to identify this, coming back up to my expression up here, is that we're always going to be interested in finding, and so by the way, I actually kind of want to scroll back up to this real quick here. When we say that we're looking for an expression and its derivative, you should recognize that that very specifically is g of x in this case right here, right? G of x and g prime of x are the expression and the derivative. This is what we're going to call u right there. When we say u substitution, we really mean the g of x component associated with how we write our chain rule right here. That'll always be our choice. Okay, that will be our choice of u in our simple u sub settings. We'll see some slightly trickier ones coming up at the end of the day here today. But to kind of get the ball rolling right here, this is what I'm looking for to identify as u. I want to just call that a variable rather than an entire expression for x right there. So what I'm going to do to kind of get things going here is I'm going to replace x cubed with a variable that I'm going to call u. So this is my substitution. I'm building a new variable that's going to help me simplify the expression that I'm attempting to integrate. In general, you should always trust that integrals are hard, and you always want to do all the work that you can to make the expression that you are integrating as simple as possible before you actually do the integration. That's what I'm doing right now. So what I'm going to do is I want to make a swap here. I'm going to swap out x cubed for just u, which is much simpler. But you should notice that what this is going to do is it's going to kind of give me sort of like two problems so far, right? If I'm going to make u be x cubed, then I don't know quite what to do with 3x squared, and I don't quite know what to do with dx. Those components are going to have to be replaced as well. If I want to convert this integral from an integral in x to an integral in u, then I need to convert everything into u. So what we can't do is just make that one statement right there. One of the things that I know is that this dx is going to have to get replaced. I need this to be like a du integral if I'm going to be putting a bunch of u components in here, right? So here's what we're going to do. This u equals x cubed, I want to come up with a description of how u changes over time, just like dx is a description of how x changes over time. So what I'm going to do here is I'm going to take the derivative of u with respect to x. It's going to give me 3x squared. And we're going to do a little move right now. So this is one of those things where in one sense I'm going to do a little hand wave, and in another sense I'm going to do a little bit of a fist shake right here. And this is an important, very important technicality right here. When we write expressions like du dx, it is very important that you understand that d dx is an operator, the derivative operator, and it is operating on the function u. What this is not a fraction. This is not du divided by dx. We write it to look like a fraction. That notation was chosen by some smart people. Even though it's not a fraction, it's not a fraction. It is not du divided by dx. Don't make me pull my crazy eyes out if you guys do weird stuff with this later. It's not a fraction, but the reason why this notation for derivatives was chosen this way is because it turns out that it works out to deal with these terms individually, multiplicatively, in a sense that will end up being equivalent to something that is also true. So what I'm going to do right now is something that is algebraically seems natural. It is technically, according to a calculus sense, not something that you should trust as something that is always going to work out for you. But in this setting, here's the uncomfortable thing I'm going to do, is I'm going to multiply dx to the other side. And I'm going to write du equals 3x squared dx. All right. Now, what you can see is that this is super helpful for us in making the substitutions that we want to make in our integral right here. It turns out that even though this is in a technical sense not quite an appropriate usage of the expression du dx, it will turn out that when we make this substitution, it is equivalent to the more technically appropriate way to make these substitutions happen here. So the parts that I can see I now have are this. So these are my substitution parts right here. I've got a way that I can replace x things with u, and I've got a way that I can replace dx things with du right here. So notice the very important part is that 3x squared and dx, those come together to just be du. I also have sine of x cubed, which we're going to be able to write as sine of u. So it seems like now we can say that our integral is actually directly equal to sine of u du. And that's easy, right? So what we've done here is we didn't do the integral right away. We stopped and we rearranged how we think of the integral so that we can put it in terms that are a little bit more easy to manage. Now I just have to say to myself, what did I take the derivative of to arrive at sine? And don't just say cosine here. I believe there should be a negative associated with this guy, right? So a negative cosine of u. Don't forget your constant of integration plus c. And as our final step, since our original integral was stated in terms of x, we have to state our final answer also in terms of x. And so it seems like we now can undo our substitution and say that our answer here is negative cosine of x cubed plus c. All right, so in our u substitution, we're always hunting for an expression where we can also see the derivative of that expression within the same integrand. We will assign our u to be the underivative expression, right? Just the original x cubed. We will compute also what is du, not just u, so that we can also substitute out our differential term. And then we should arrive at a much simpler integrand that we can actually perform integration on. Right? So let's do the same thing in the next example. Next example, a little bit more hairy, a little bit less obvious. We're going to have to make one additional little modification to this guy right here. But otherwise, it'll follow pretty simply. Should say follow the same kind of pattern right here. So I guess the things I'm seeing here is I got an x, I've got a division, I've got a square root, and gosh, every time I see like a square root of something complicated in an integrand, I'm like, damn it, this is going to be hard now. The good news for us is that x squared plus 1 has a derivative of 2x, and that seems very, very close to just x like we've got right there. It's going to be off by a factor of 2, but we're going to be able to shuffle around that factor of 2 to be where we want it to be here. So again, even if I can't quite see where I'm going with this one, what I can see is that x squared plus 1 has a derivative of 2x, and that seems like the x that I'm seeing right there. So that's my good indicator that u sub is going to be a good move for this guy here. So for my u sub then, I'm going to let u be x squared plus 1. Another thing I want to point out right here, letting u be x squared plus 1 rather than just letting u be x squared, there's no reason for me to not kind of like encompass all of that information into u right there. I'm trying to make this as simple as possible. So often your goal should be to incorporate as much of an expression into u as you can, because leaving that extra plus 1 out floating out there, I guess we could probably still make this happen, but it's just leaving more terms in your integrand. I am always looking for the simplest possible integral that I can ever leave myself with. And so if at all possible, I always want to include extra stuff like that plus 1 or something in my u, so that when my integral will look as simple as possible. That plus 1 is just going to go along for the ride with us here. So hopefully what you can see from my previous example is that I'm going to kind of just skip this middle line of work right here and go immediately to writing a differential statement right here. You should notice that all this amounts to is replacing u with du, replacing the x expression with the derivative of the x expression, and tacking on the additional multiplication by our differential dx term right there. So I'm going to do exactly that here. It looks like du equals 2x dx. This is really good for us. This looks a lot like what I have. I have x times dx in my integrand. Here's x times dx. My only little bugger about this is I've got this extra multiple of 2 right here. So I think what I want to do is I typically, for myself, I like to force the x stuff to look exactly like what the x stuff is going to be in my integrand right here. Therefore, I'm going to make this instead 1/2 du equals x dx. And now I have an exact replacement right there. X dx is going to get replaced exactly by the x dx there. I also have the term underneath the square root is going to get replaced exactly by u right here. So let's go ahead and do our replacements. And I guess I'm going to write one extra line here just because I do want to remind you guys, these dx terms, they're not, I feel like I spent like my first year of calculus or like my first introduction to integration feeling like that dx was sort of like a note telling me, oh, the variable of integration is x. It's not just a label, right? It's actually a multiplicative term. Remember that this is like a length times a width. And that's one of the 2 components of the area of a rectangle right there. So that dx is a multiplicative term, and since we're multiplying by a fraction, this is the same thing as writing our integral like this. I never really write my integrals like this, but there's some, like I've seen textbooks that always include the dx as like a multiplicative term. If there's ever like a fraction, to like mash it in up there. It always makes me feel a little weird, but there's nothing wrong with that. That dx is a multiplicative term. You should treat it that way. So now I think I can go ahead and make my substitution here. Myself some room here. So let's swap out all of our terms that we've got. It looks like the numerator is just going to become 1/2 du. It looks like the denominator is just going to become square root of u. So that's pretty nice for ourselves. So let's go ahead and rearrange some terms since I don't really like look this. Every bit of this isn't really where I want it, right? I know that constants don't affect integration, so we can pull those out front. I never really like including my differential term like within a fraction. I always push it out to the end out there, so I kind of would prefer to see my du right there. That's personal preference though. If you like it in the fraction, go for it. The other thing I can see is that my remaining terms are 1 over root u, and this, I know that in general, 1 over isn't how I like things in integrals, and square root symbols aren't what I like in integrals. I'm going to think of this as a u to the negative 1/2 because now I get to use the power rule. That's just my better representation of that same expression right there. So this is now a u to the negative 1/2. And now we're in great shape. Now we just have a one-step power rule to undo this guy. So what do we got here? It looks like now this 1/2 still floating along for the ride out there. I'm going to see here, I'm going to add 1 to the power. So this is going to become u to the positive 1/2. I know that if I were to take the derivative of this, it would bring down a 1/2 right here. I want to have one whole copy. Remember, this 1/2 is already handled out the outside. Ignore 100% of this 1/2 right here. I have one copy of this guy right here. I want, when I take this derivative, to result with one copy. So I'm going to stick a 2 out there as my additional coefficient, so that when I take this derivative, 1/2 times 2 becomes the 1 that we have sitting right there, right? I often will do this where I will make sure that I get the power correct on my variable. Then I will stop and sort of think to myself, how do I make sure that I get that constant coefficient right? I never try and do both those steps at the same time. I make sure that the power is correct first, and then I make sure that the constant multiple is correct every time I'm doing kind of weird fractional power rule stuff like that. And finally, we can stick our plus c out there on the end. I'm going to go ahead and distribute through the 1/2. So it looks like we're just really getting left square root of u. 1/2 times an unknown constant is an unknown constant. So I'm just going to leave that as c. Very technically, these two c's differ by a factor of 1/2. But if we were going to go solve for that c with an initial condition, it would work out appropriately either way right there. Any unknown constants like that are perfectly, it's acceptable to allow them to like absorb other constants in there. Once we go to solve for them, we'll always get our correct value here. And so what does it look like we're ending with? Remember that it's always our responsibility to get back in terms of the original variable that the problem was stated in. So I now just, as my last step, just want to undo my u sub that I did right there, throw that x squared plus 1 back in. And it looks like we have now performed the integration right there. We used u sub to perform integration on an expression where we saw an expression as well as the derivative of the expression, give or take a constant multiple, right? So kind of your small lesson to learn from this one right here is don't worry too much about being off by a constant multiple. That can always be shuffled around a little bit right there. So the fact that that was a 2x versus just a 1x, that's an insignificant issue, constant multiples. It's the variable components that we have to worry about matching up. If that was, for example, x cubed down there, I literally couldn't do this integral, right? If that was an x squared up there, I actually can, and we're going to see an example that's going to look like that one later, but don't worry about that one right there. So there we go, our first two u subs together here. Now, one of the things that happens with u sub is, I'm going to come back up here. If I give people this derivative at like the end of a Calc 1 semester, most people like forget that this is even a chain rule application right here, right? Popping out that extra factor of a 3 right there is something that becomes very, very natural to us. It's sort of like a trivially easy step in that derivative right there for most of us after Calc 1. And very similarly, once you've done enough u sub, which you all, I'm certain, will end up doing this week, you will also come to find that there's some u subs, the integration version of the chain rule, where you also won't even necessarily think of it as doing a u sub. You'll just do it naturally because the only thing that was affected was a single constant multiple right there. At least over here, it was like more x stuff, right? That was just a constant of a 3. It's pretty natural for us to pop out the 3 as we take the derivative, right? So that's why my heading right here is rather than going from easy problems to hard problems, as I've titled them, I'm saying these are our easy examples. Here are some more easy examples, but the category for these are things that are, I don't even remember often that these are u subs because I don't even write out the u substitution for these. These are ones where I'm just like, oh yeah, it's going to introduce a factor of 1/3. Got it. And I'm done, right? It's just a constant multiple that's going to be affected. So let's write these out. But I do want to say to you guys, these are things where like I expect you to show work, right? Like that's, I hope that's not a weird standard that I'm going to hold you guys to this semester. I expect to see work. Like on this one right here, absolutely. You got to show me the work of your U sub, especially for the second one. This one right here, honestly, maybe you guys could just do that one in your head since it's x cubed and 3x squared. But here there's like constant multiples to deal with. There's square roots, there's fractions. This one's hairy enough. I expect all of you to always show this work. These guys down here, if you can just straight up do these, I kind of get that. These are ones where I'm not going to yell at you if you didn't show work right here, right? But let's write them out to make sure that we do see that all that's happening here is just a constant multiple that's being affected. So here what I'm going to say is, okay, e to the 3x, technically it's a composite function. Technically I'd need to show a little bit of u sub for this, so I'm going to let u be 3x here. In that case, du, I take this derivative and I just get 3 dx right there. I don't have a 3 dx, so I'm going to rewrite this as 1/3 du equals dx. I now have substitutions that I can make for all of my parts. So now I think I can say this should be e to the u times 1/3 du, which I will more appropriately write as 1/3 integral of e to the u du. And we all know that the integral of e to the u is just e to the u. U was 3x. And there we go, right? So I'm hoping that you guys can see, and here's kind of the way that I think about this. I know that if I were to take the derivative of e to the 3x, it would pop out a constant multiple of 3. Therefore, if I'm integrating e to the 3x, it should pop out a constant multiple of 1/3. The 1/3 would be canceling with the 3 if we did the derivative in the integral to leave us back at the integral expression right there. So again, I'm hopeful that as you guys practice a little bit of these right here, like this example becomes so obvious and natural that I almost hope you don't treat this like a u sub in the future, because you're used to enough of seeing this concept of the chain rule and the chain rule in reverse that you don't actually necessarily have to show work for that one right there. Right? Very similar to this next one. This next one's a smidge hairier, but not by a whole lot right here. Again, I can see that I've got an expression underneath the square root. Don't quite know what to do with it, so maybe let's just, but since it's only constant multiples that are being affected, let's just call u 5x minus 3. In this case, du would just be 5 dx, right? The integral of this expression is just 5. It's all right there. Stuck my differential term dx right there as we've been doing. In fact, I'm not going to do it this way. I'm going to do this a little bit of a different way right here. Here's the way I'm going to do this one. What I'm going to do here, this is just an alternate way that you can shuffle around your constants. I'm just going to do it once just for the sake of showing it, since some people prefer to do it. In some circumstances, this turns out to be maybe a slightly slicker thing to do. I rarely do this, but I just want to show this as an option. What I'm saying to myself right here is I need to have a 5 dx and I only have 1 dx in here, right? So what I would need to do then to handle my constant in a different fashion than we have before is introduce a multiple of 5, right? So here's the way that I'm going to do this. What I want to be able to write here is I want to have this. Therefore, if I'm going to multiply my original expression by 5, to undo that, I also need to divide my original expression by 5. So all I really did here is I multiplied by 5 over 5. I used the 5 from the numerator to join up with the dx to make my substitution happen. I'm using the 5 from the denominator. Well, I'm not using it. I'm just letting it go along for the ride. It had to be incorporated to match up right there. All right, so again, this is just like an alternate way to handle a constant multiple. It's really not a big deal. If this seems more satisfying to you, then do it. It's probable that you'll see in a textbook or in something online somewhere this semester, someone will probably handle their constant multiples in a u sub like this. It's not an unreasonable thing to do. I'm just typically partial to the manipulate your differential expression rather than manipulate your integral expression, but it doesn't matter right here. The point is, I'm now good to go on with my integration here. 1/5 times the integral of the square root of u times du, right? That is my du expression now, 5 dx right there. As with before, I don't like radicals, the square root symbol. got caught halfway between an integral and a square root right there. I don't like the radical symbol in my integrands right there. I would rather think of this as a u to the 1/2, so I can use a power rule. And now I know that I'm going to add 1/2 to the power, so it's going to become a u to the 3/2. But I know that if I were to take the derivative, a 3/2 would pop down here, whereas I only have a 1 right here. So I'd like to introduce a 2/3 to go ahead and cancel that guy. So now when I take this derivative, I'm just going to get back u to the 1/2. And again, I'm ignoring the 1/5 completely. Those are just constant multiples going along for the ride. And as with before, I now think that I can rewrite this. So multiplying fractions there, 2/15 times 5x minus 3 to the 3/2 plus c. And again, I'm letting that plus c absorb some more constant stuff right there. If we were going to be given an initial condition to go solve for c, we'd still get it correct regardless of the way that we did that guy right there. So it looks like I've got my final expression there, post u sub for that guy. So again, notice that the only thing that was happening here, I think the highlight of why I say these are technically u sub but I forget, is because the only swap that's really happening here is just a constant multiple. That's really the only thing that was ultimately affected right there. I don't know. This one was weird enough. I think getting to 2/15 is a little bit awkward right there, but certainly like this guy right here. I think this is something that I'm hoping we can just do in our head relatively soon right there, since it's just affecting a constant multiple right there. But these technically are u sub in the same way that this guy right here is technically a chain rule, but that we don't even see it because we can kind of just walk right past it because it's a pretty natural operation for us to do there. All right. So we've done some of the easy ones. We did some of the just constant multiple basic ones that you could maybe do a shorthand version of, however you choose to do that. Let's go ahead and look at some slightly more difficult examples. I'm going to do two slightly more difficult examples. One thing I also want to point out so far is that the 4 that we've done have all been indefinite integrals. We've got our plus c on the end. We're also going to end today with some definite integrals to identify a little bit of caution that we're going to need to exercise when it comes to definite integrals. There's some mistakes that are easy to make that we want to avoid, so we're going to talk about those as well. So our harder examples right here. I'm going to look at the integral of tangent of x. The first thing I want to ask myself is, do I know what the antiderivative of tangent is? Have you ever taken a derivative and gotten out tangent for your derivative? And the answer is no. Tangent, the derivatives of tangent, we know, we're all a little bit funkier. In my experience, everybody remembers their derivatives of sine and cosine, and then tangent, secant, cosecant, cotangent. Everybody has to stop and be like, oh, wait, what? Or look them up, or do your quotient rule, or whatever else it is out there. They're all like little funkier ones. I know that the derivative of tangent is secant squared, for example, right? We're getting squared terms cropping up in there. But the bottom line is no, there's not a direct antiderivative for tangent that we have seen before. So what we should ask ourselves then is, well, what are we going to do, right? Does this look like some form of u sub that I could do right here? Like, for example, should I do something like u equals tan x? If I did, then I would get du equals secant squared x dx. Is that going to work? And on the one hand, what I want to say to you is this. One, you should be doing stuff like what I just wrote, even though it's wrong. And the reason you should be doing this is because you need to just try things. Integration is hard, and it's most of what this class is about. It matters that you are comfortable flopping out a guess on paper and seeing if you can work it out to the end. And if you get stuck, don't be disappointed. Most integrals are going to be hard. Most integrals you're going to make mistakes on, you're going to make wrong guesses on. You need to try stuff. That's how you develop intuition about what is good to try and what's bad to try, is by trying lots of things. So do stuff like this. What I just wrote isn't going to work out for us, but it's not bad for me to have thought that. That's not an unreasonable attempt to make right here, all right? So this isn't going to work because I have no way to construct a secant squared of x component to somehow naturally exist in here. If this was the integral of tan x times secant squared x dx, then this would be a super easy, trivially easy u sub right there. It would be the expression and its derivative sitting right there, right? We don't have that, though. We're missing a required component. So it doesn't look like this is going to work out for us. All right, so let's go ahead and say I don't have the pieces I need. There's no secant of x right there. Secant, ooh, squared of x, goodness. So what do we do? Well, I think that we should all pull back to trigonometry class here and think about what is it that you did every time you were in trig class and you're dealing with an equation or expression that's in terms of trig expressions that made you feel ever so slightly uncomfortable like tangent does. And I think that I am hopeful. It's typically the case that when I bring this up to people, everybody tells me the same thing. Everybody's on board with this, which is I know that in trig we learned that there are 6 trig functions essentially, but that's ridiculous. There are 2 trig functions, sine and cosine. The other 4 are just made up of modified versions of those 2. Sine and cosine are the true trig functions that we're interested in here. So what I think I'm going to do here is I'm going to write this as the integral of sine of x over cosine of x dx. Now, here's the situation that we're in. I know that this is a good move for me to make because I know that what I'm looking for is a situation related to u sub where we have both an expression and the derivative of that expression both involved right here, right? And the great news is that both sine and cosine are essentially derivatives of each other, right? The only difference is that one of them will introduce a negative, but as we learned in our previous 2 examples, a constant multiple, negative is just a multiple of -1. Constant multiples don't make a huge impact on our ability to perform u sub. So I'm not even worried about that negative being introduced right there, right? So this integral of sine over cosine dx, this seems to me to be much, much more appropriate for a u sub scenario, right? So let's pick some stuff. Again, this is one of those things where you should not expect to be right all the time. You should expect to have to try some stuff. So I'm going to try some stuff. I'm going to flop out a guess. Maybe what we want to do is maybe we want to let u be sine of x. In that case, for du, the derivative of sine is cosine of x, and I'll get my differential dx tacked onto the end right there. Is this going to be an appropriate u sub to do? The answer here is no. And it's sneaky that it's no. But what we got to remember is that this dx is multiplicative. Officially, this dx, if it belongs anywhere in this fraction, it's up in the numerator because it's being multiplied by this fraction. What I have in my integrand is dx divided by cosine of x, not dx times cosine of x. So it doesn't look like this is going to work out either. The cosine is in the denominator, not in the numerator. We don't have a dx times cosine of x anywhere in our integrand. So this looks really, really, really close to what we want, but it turns out that in this case, that's not going to pan out. What I know is that this sine of x times dx really means that sine x dx needs to be my du part, not my u part right here. So now let's go ahead and let's flip our choice of u, and let's see if we can actually make this guy work out here. So I'm going to now make my 3rd attempt at doing a u sub here. And now I'm being a little roundabout on this one on purpose, but the point is there's absolutely going to be problems this semester that are going to take you 7 tries and you're not going to get it right till your 7th attempt at u subbing or trig subbing or integration by parts or blah, 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 all the techniques that we're going to get. Eventually, you're going to have a large bag of techniques this semester, and identifying the correct one, it's going to take some guesses, and that's okay. So I want to break you into the idea that you're going to write down some wrong stuff, and you need to like get over that in a heartbeat. There's nothing wrong with being wrong. There is something wrong with being wrong and then quitting. Don't do that. Keep trying new stuff, right? Now I can see that my only real choice left is to let u be cosine of x. If I make that choice, then du is going to be negative sine x dx, and this feels good to me. I do have a sine x dx involved in my expression here. I'm going to go ahead and move my negative over to the other side because that's just how I like to manage my constant multiples in these scenarios right here. But again, you might have a different preference for that. This guy, it seems like, is going to work out for us right here. I do have u being replaced. I do have sine being replaced. I do have dx being replaced. All my replacement parts are incorporated here. So it looks like I can now rewrite this guy as sine x dx. That's just becoming a negative du times. So the sine x and dx have been accounted for. They're just du. So I've got a 1 left on top. Cosine is what we're now calling u. And so now I just have the integral of 1 over u du. I've greatly simplified what our integrand looks like. This is an expression that I know the antiderivative of. I can now go ahead and actually integrate this and get the negative natural log of the absolute value of u plus c. And now all we got to do is undo our substitution and we're good. Remember, by the way, little technicality, the integral here is always going to introduce this absolute value because 1 over u has a domain of all real numbers except for 0. Natural log has a domain of only positive numbers. We want these domains to match right here. So this natural log of u gets the absolute values so that, as with 1 over u, 0 is the only element of the real numbers not included in its domain right here. So these are absolute values that you get from this integral right here. But other than that, I think that this is, in a sense, a straightforward hard example right here, in the sense that it's hard because at first glance you have nothing to do. But once you rewrite this in terms of sines and cosines, it's obvious that there's only two possible choices. And by trying one and getting it wrong, I tried the other and got it right there. So this is what I would think of this as an easy, hard example. It's not directly obvious what to do, but once you get going a little bit, the actual calculus itself panned out to be pretty easy right there. All right, so negative natural log of cosine of x plus c. And by the way, for all of these, never forget that you can take the derivative of every single one of these answers, and you should be getting back exactly what's inside of the integrand right here. If I take this derivative right here, notice that I'm getting negative 1 over cosine of x times the derivative of cosine of x, right? The derivative of the outside function is the derivative of natural log, gives you 1 over the inside, times the derivative of the inside, and that's going to give me negative 1 over cosine of x times negative sine of x. The negatives cancel, and that leaves me with sine x over cos x, right? So remember that you can always go ahead and check these guys for yourself and convince yourself that these are correct. But like, I wouldn't guess this for the integral of tangent. That like, to expect for tangent's integral to involve a natural log is weird. And I think that everybody's on board with that statement right there, right? But easily verifiable with a quick derivative right there. Cool. So remember, you got to try stuff. That's the lesson to learn from this one. It's okay to flop out some guesses and for guesses to be wrong. Keep going. There's really only a finite number of guesses that you're going to be able to make in terms of u sub here. And when we get to our slightly more complicated version of u sub, that's still going to remain true. You're going to have slightly more guesses that you could make, but still it's like, even if there's only 7 possible choices of substitution you should make, I guess 7's more annoying than 2, but also it's like, it's a pretty finite number. It's not like you can't just keep trying things till you found the thing that worked. So hopefully we develop intuition so that we're not making blind guesses, but don't feel uncomfortable making a good guess. Now, our next one, this one is, I'm going to put this in the category of actually a little bit harder right here. I think that tangent one was pretty okay once we got in terms of sine and cosine. This one's a little weirder, but I like this one a lot. So in this guy right here, I'm thinking to myself, I wish I had a product rule. I guess this is the sentence I'm saying to myself right now. I wish that there was a product rule for integration, since I have the product of two functions inside of my integrand, x to the 5th and square root of x squared plus 1. But we don't. There's just no such thing as a product rule for integrals. And so, well, there sort of is. We're going to get it. And the 7.1 is sort of the product rule for integrals, but it's weird. It's not going to work out quite the same. So what can I do here? Remember that our goal is to find an expression and the derivative of that expression within the integrand. If I were to pick x to the 5th to be u, then I would be getting 5x to the 4th that I would want to be sticking in somewhere, but I don't see how I'm going to make 5x to the 4th do what I want underneath the square root. On the other hand, if I chose x squared plus 1 to be u, then I'm going to get a 2x for my du term, but then what am I going to do with the rest of the 4 powers of x that I have hanging out outside of the square root? Both of these choices don't necessarily seem like they're going to be able to do it for us directly, right? This is another great example of where you need to just try some stuff and trust that something might work out, all right? So here's the way that I like to think about this one. Neither of these choices, x to the 5th, x squared plus 1, neither of them seem fantastic to me. But the one thing I'm thinking is the square root in this integrand, that's screwing me up more than having an x to the fifth is. I am more unhappy about the square root term than anything else in here. That's what makes the integration hard to me, right? So what I'm thinking is that's the thing I'm the most interested in making as simple as possible is the square root term. So that says to me, my intuition says to me, man, I wish that square root wasn't there. So let's use u sub to get rid of the square root difficulty right here. So the choice that I think I want to make is u equals x squared plus 1. Now, I feel good about this because this is going to help simplify my square root expression, but I feel bad about this because I know that I'm not going to make all my other parts work out sort of perfectly with this, right? So what are we going to get to partner up with this? Let's see. We're going to get a du equals 2x dx, and I'm going to do my typical moving the constant multiple around, x dx. So let's do what we've got so far. Let's do this substitution that we so far have and see where we land. What I can see here is I want one of these 5x's to partner up with the dx, right? So I'm thinking I'm going to rewrite this to myself as x to the fourth integral x squared plus 1 times x dx, right? All I did was just pick off one of those x's and put it to buddy up with the dx. I'm just trying to build this so it looks like my substitution. So here's my deal. I've really got now, once I start doing my substitution, I'm going to do like a partial substitution here. I can deal with the square root term. I can deal with the differential term, but we're still floating around with an x to the fourth. We can't have these like mixed variable integrals right here. I need to either be in u land or I need to be in x land. And right now we're half and half. But on the other hand, I would like to encourage you guys to write lines like this. Like this is a sort of like weird intermediary step right here, where we can't do anything with this integral as it stands. But it's sort of like helping me say like, okay, what have I dealt with so far? I've dealt with the square root. I've dealt with the differential. Now that allows me to like really focus my attention on saying, what the heck am I going to do with this x to the fourth here? What I want is I want an expression for x to the fourth in terms of u. Do you see something on the screen right now that will allow you to create the quantity x to the fourth in terms of u? Here is a good moment where you should pause the video and figure this out for yourself for a second right now. And now I'm going to do it. So the only place that I see a reasonable expression on the screen where I could relate x and u without there being some differentials involved is with this guy right here, right? So I know that u equals x squared plus 1. I want an expression for x to the fourth, right? I think I can force this to happen. Let's subtract the 1 over to the other side. And it looks like I can just square both sides. Using our u substitution expression, a modified version of it, it's also giving us a way that we can rewrite x to the fourth, not just x squared plus 1. This is pretty cool right here. So we're sort of double using our u sub for two different purposes here, which is pretty neat. So I now have an expression for x to the fourth in terms of u. I'm pretty happy about this. So now it looks like I can replace this guy, u minus 1 squared times the square root of u du. So on the one hand, we've done a good job in the sense that I have fully rewritten an x integral in terms of u. On the other hand, we need to ask ourselves, did this improve our ability to actually perform the integration? Like, there's tons of u subs I could write that just lead me to another non-integrable integral. That doesn't help. Are we in an integrable status right here? And it looks like the answer is yes. And the reason why the answer is yes when the answer before was no is because this square root term is really hard to deal with. It's really a composite function, right? It's really the outside function is the square rooting, the inside function is the x squared plus 1. Managing composite functions with integration is hard. Managing simple functions, simply the square root of u, there is no composition of functions there. That makes this much more manageable for us. So now I think because this is a non-composite function here, I think I can do this. So there's two important things that I want to do. Uh-oh, why did I just lose my pen there? Okay, there we go. Is I'm going to do two things. One, I'm going to expand u minus 1 squared. And I'm going to rewrite square root of u as u to the 1/2. And it looks like now I can just do the multiplication right here. I'm just going to expand this guy and do my integration term by term. So it looks like I'm getting the integral of, that's u to the 2, an additional half power makes that a u to the 5 halves minus 2u to the 3 halves plus u to the 1 half du. I now have an integral of the sum and difference of constant multiples of powers of u. So it looks like I've just got 3 power rules now that I have to do with integration, and we're done. Excuse me. And then sub back into x, and then we're going to be done here. So let's do it. I can see that when I integrate u to the 5 halves, I'm going to get I'm going to add 1 to the power. That gives me 7 halves. But I know that when I take a derivative, it would pop down a 7 halves. I don't want that, so I'm going to introduce a 2/7 as its coefficient right there to counteract that. On the second term, I'm going to get a minus 2 times, and again, I'm writing the minus 2 so that I don't have to think about it. That now is 100% dealt with. The only thing I'm considering is 1 copy of u to the 3 halves. The doubling is already accounted for. So 3 halves is going to become 5 halves because we add 1 to the power. So therefore, I need to introduce a 2/5 to counteract the power that would be popped down from the derivative right there. On our last one, finally, I'm seeing I do just have a positive 1 copy, so I don't have any extra constant multiples to deal with. The power is going to increase by 1 to 3 halves, so I'm going to introduce a 2/3 to counteract the power that would get popped down if I were to take the derivative, going back up. And of course, our plus c out there on the end. Never forget your plus c's. And I think we're done. I just got to rewrite this thing in terms of x and simplify some constant multiples, and we got this guy. So 2/7 times, gosh, I don't even remember what u was by now. U was x squared plus 1. So 2/7 times x squared plus 1 to the 7 halves minus 4/5 x squared plus 1 to the 5 halves plus 2/3 x squared plus 1 to the 3 halves plus c, right? So, and I think this is also awesome because, like, this is a pretty scary expression. If I just handed you this thing, you should be like, oh, crap. But this came out kind of naturally from an integral that we originally couldn't handle, right? So this is a great u sub example right here where we used our u sub for really 2 alternative purposes out there. So this is another great reason why I say to you, you need to like have a little faith when you're doing this. You need to trust that probably something's going to work out somehow. You might need to try several different choices of u. You might need to do some additional algebraic rearrangement to find all of the necessary substitution cases that you need to make. But I mean, I really enjoy these. If this doesn't feel like a fun puzzle to you, then I kind of think that you're crazy that you're already in Calc 2 without enjoying the puzzle that is calculus. This is really cool. It's like finding what parts you have, finding what parts you don't have, and using the parts you do have to make the parts that you don't have. We're forcing it to happen here, and that worked out pretty dang nice right there. And by the way, notice this could have worked out with any power that we were sitting there with right there. All we had to do is make the appropriate power on both sides relative to this expression right there, and we could have made that happen. It helps to make sure at least that that's a whole power so that we can at least expand that expression for the distribution. But again, the point here is that was pretty cool. We built the parts that we needed for ourselves. And I guess before I walk away from this problem, the last thing I want to say is I think that this line right here is really important, where on the one hand, this is sort of like a bad line of calculus. Nobody should ever leave a standalone line like that because we're mixing variables that are supposed to be directly related to each other. But on the other hand, there's nothing wrong with saying, okay, where am I at so far? This is my so far line of work. It's an intermediary step that could never be standalone a good step, but it did help me see I know I need a way to write x to the 4th. So it helped me see something by doing a couple of the steps and being done with those, and then focusing on another step. A big lesson that we're going to take away, and I shouldn't say a lesson, it's more like a theme of this class, is there's going to be problems that are big enough that you can't just do the problem. You have to break problems down into lots of small, easy problems rather than one big problem and handle those problems one by one. Lots of small problems, way, way better for you than one big problem out there. And that's exactly what we did. This is our divide and conquer technique right here. We broke it up and we handled each part individually. Cool. So there's our other good hard u sub. So All I got left for you here is let's do two more examples. And these two examples, the lesson associated with these is we need to be careful when we have bounds of integration on our integrals and we are performing U sub. We have got to be careful. There's two different ways that we can responsibly track the variables that we're using right here. And that's why I've got two examples so I can show you one way that people handle it, another way that people handle it. This one's a lot more split. I'm going to scroll back up real quick. When I did this no, when I did this right here, where I did the 1/5 and the 5 a minute ago, I feel like less people do that. I feel like this is more like a 90% of people do their algebraic manipulation here, and like 10% do their algebraic manipulation here. I don't think that's like a 50-50 split. On the other hand, the two techniques that I'm going to show you to be careful with your bounds of integration here, I feel like this is more of like a 50-50 split. Well, maybe not 50-50, but a lot closer to an equal split than the previous difference in technique for being careful that we saw up above. So let's go ahead and hit these two guys right here and see what the risk is. What's the thing that we've got to be careful of in these situations? That's the thing we want to watch out for here. So remember, in U sub, we're always hunting for an expression as well as the derivative of that expression. The other lesson that we learned with U sub is that often what we want to do is take difficult composite expressions like the square root of x squared plus 1. Those are things where we have great value in reducing them down to simple expressions where they're no longer composite. The square root of u is not a composite expression. The square root of x squared plus 1 is a composite expression. It's really two different functions nested together, right? We don't like that. That's what makes things hard for us. And so that's kind of our intuition as to how do we know what the selection is that's appropriate in our u subs, right? So when I'm looking at this guy right here, I see that. I see that we have a composite function, e to the 1 over x. It's e to the x composed with 1 over x. That's a big red flag to me right there that I don't like that 1 over x being there, that's likely what I'm going to want to make as my choice for u. But I'm going to do one thing to help myself out a little bit right here is I also maybe don't necessarily want to think of this as like a fraction right there. Maybe I want to be rewriting this as like an integral from 1 to 2 of e to the 1 over x times 1 over x squared times dx. I'm just separating out my parts right here. I'm just getting a different look at this same integral here, right? So again, this composite function suggests to me that 1 over x is a good choice for you, and I'm hoping that what you have remembered from last semester is that the derivative of 1 over x is going to be this other part that we've got right there, right? That x squared stuff right there. So I'm thinking that this is going to be a good choice. So I'm going to let u be 1 over x. By the way, we know that this is x to the negative 1. This allows me to think of it in terms of a power rule. When I take the derivative, a negative is going to pop down in front. We're going to reduce the power by 1. So my du here should be negative x to the negative 2 dx. dx, so this is the x side of things over here. And this is negative 1 over x squared, right? So I do think I want to move that negative. So this is great. Everything's working out very cleanly for us right here as far as our u sub goes. I've got 1 over x squared dx just like my integrand. I'm going to be able to convert my composite function into a non-composite function, just a simple function, just e to the u now. So I feel like we're going to be in pretty good shape right here. So let's go ahead and do this, but ever so importantly, we have to remember what 1 and 2 represent. Since this is a dx integral, this says that x is going from 1 to 2. This is not u values. These are x values. I need to remember that. So one of the ways that we can handle this is like this. One of the ways that I can do this is I'm going to keep writing my integral like this, but I am going to be very careful. And I'm going to explicitly state that these are x values because I am a responsible mathematician. Now I'm going to write my substitutions in here. I've got my e to the u. Over here, I'm just getting a negative du from all that stuff. I'll stick my negative out front. That's an easy integral right there. But notice the very clear thing that I did here. I made it very obvious that while this is a u integral, the bounds of integration are explicitly x values, and I don't want to conflate those two things. So now let's do the integration. The integral of e to the u is just e to the u. That's all that happens right there, right? That was the negative integral of e to the u, so I got negative e to the u plus, oh wait, excuse me, no plus c. We've got a definite integral right here. I'm like so proud of myself for remembering all my plus c's that now I'm going crazy with them. So I'm just getting negative e to the u, which I, evaluated from. And again, I'm not going to write 1 and 2. I am writing that x equals 1 and x equals 2 so that I know to not attempt to evaluate yet. Now I am going to go back into x land. I've got my substitution right here. U was 1 over x. And now I am in good shape to go ahead and evaluate my integral. So the key here is you have to remember that you moved into a whole different universe when you performed u sub, and that the bounds of integration that were given to you are in your original universe, and you need to not confuse which universe you're in. You're either in u land or you're in x land, and we can't mix those and match those, right? So now I think I can actually go ahead and evaluate this guy. I'm going to do my upper bound, e to the 1/2, minus my lower bound, which should just be e to the 1. And I think I could in total then write my answer as e minus square root of e right there. Right? Notice I'm just multiplying the negative. Negative is a constant multiple, so I left it factored out front for my evaluation of my function here. Then I distributed it through. E to the 1/2 is the square root of e. E to the 1 is just e. But when I multiplied the negative through, the e became positive. The square root of e became negative right there. So it looks like this is our final value here. I think this is a good exact answer right here. I'm sure there's a decimal we can get for that. I care about those a lot less. Okay, so there's our first one right here. And again, broadly, the lesson of these two problems is you have got to be careful with your bounds of integration. It is incredibly common for people to forget to convert back to x and just evaluate this expression from 1 to 2, which wouldn't be appropriate. In our last example of the day right here, this is a very, very good one. I really like this problem right here. And in this one, I'm going to still be very careful. I'm still going to be very responsible about being careful with my bounds of integration, but I'm going to handle it in a very different way. And again, it's very typical to see both of these right here. You should expect the book to do both things. I expect when I'm grading to see both things from you guys. So this is pick which one you're comfortable with. Pick the one that you will be consistent with. That's the key. Consistency is the hallmark of a champion. Don't do things different every time. Pick a set patterns that you know what to expect from yourself. That'll help you out a lot. So our last integral of the day right here, x times the square root of x minus 1. We're now back in a situation where if I were to say to you, we're looking for an expression and its derivative, I don't see that here because each of these is a polynomial of the same power. So how can one possibly be the derivative of the other? So while I don't see a u as well as the derivative of a u in here, similar to the problem that we just did a moment ago, I do see a composite function that I don't like. The fact that this is the square root function composed with the subtract 1 function makes this a difficult expression to deal with. Composite functions are kind of your enemy when it comes to integration. We don't want them because we don't have a chain rule for integration. That's what the chain rule does with derivatives. It helps us deal with composite functions. We don't directly have a chain rule, or not quite yet. We're going to get another tool that's going to be something like this here. But it's not going to be till the beginning of chapter 7, and it's not going to do quite the same type of job. So again, I don't see the first thing I generally look for in u sub, which is a function and its derivative, but I do see a composite function, and I don't like composite functions. So my intuition says to me, the only guess that I can reasonably make here would be to say, let's let u be x minus 1. That's not a super exciting transformation right there. All this literally says is shift everything to the left by 1. Take all your x values and subtract 1 from them. That's all the new values that we're considering here. Will this help me? Let's go ahead and see. If I were to do this, hey, this is our nicest, easiest differential swap that we've ever had right there. These functions both have the exact same slope, 1, right? U and x minus 1. So we get du and dx are equal to each other. What do we have so far? Well, it looks like this should be the integral from, and again, I'm being responsible. So I'm going to write my variable that's associated with these values here, x from 1 to 2. I don't know how to write x yet. I do know that the square root of x minus 1 is now going to be written as the square root of u. I do know that dx is just du. So what I need is I need x. Well, I have a way to get that, right? Similar to what we did before, I'm going to use my substitution in a second different way. So let's go ahead and add 1 to both sides. And it looks like the way that I could rewrite x is as u plus 1. Oop, that's not what I'm writing right there. What was that? X equals 1 and x equals 2. X I can write as u plus 1. Square root of u, I've learned my lesson by now. I know I want to write that as its power version. And like radicals are very rarely useful to us. We will see a couple trig sections are going to come up this semester, and hopefully you guys know that right triangles mean that there's lots of square roots by nature of the Pythagorean theorem. There will be one sort of grouping of integrals we'll use this semester where we will leave things in square root form rather than going to like a power rule setting there. But that's kind of a special case in my mind. So, as promised, I want to deal with our bounds of integration slightly differently here. So I want to show you a different way that we can transform our bounds of integration. So rather than converting our integral expression to being in terms of x at the end, I can instead convert my bounds of integration to being in terms of u. So what I'm going to suggest here is that if x is 1 and if x is 2, then if we use the known relationship that u equals x minus 1, then that's going to tell me that x equals 1. Well, if x is 1, then that gives me u equals 0. And if x is 2, 2 minus 1 tells me that u equals 1. These are the equivalent versions, right? If x is 1, then u is 0. If x is 2, then u is 1, based on the substitution that we have set up for ourselves. So in this case, what I'm doing is rather than this line right here, where we converted from u land back into x land so that we could evaluate, I won't do that in this case. I'm going to end this integral in u land because I now have bounds of integration that live in u land right here. Right? So in this case right here, I have fixed my mixed variable problem by, instead of going back to x land, by just remaining in u land and converting all of our information into u rather than just the integrand into u. All right? So now I'm going to rewrite our integral as, so what do we got here? I now know that our bounds of integration are u equals 0 to u equals 1. I know that I can multiply out this expression right here and then just do some power rule stuff. So it looks like I've really got u to the 3/2 plus u to the 1/2 du. And I'm cruising now. Now I'm just doing a little bit of integration. So what do we got here? I've got a, let's see here. We're going to get a u to the 5/2, adding 1 to the power. That means I need a 2/5 out front to counteract the 5/2 if we were to take the derivative moving back up. Similarly, u to the 1/2, I add 1 to the power. It's now u to the 3/2. I need a 2/3 to counteract what would happen with the derivative. It would pop 1 down from the power. And I'm going to evaluate this guy. I just get to go straight into evaluation, right? I don't have to deal with any other, we don't need to go back into x land because this is a definite integral and we converted our bounds of integration into u's terms. I can tell you guys that I rarely do this technique right here, but it's not because there's anything wrong with it. This is just a consistency thing. I have done about 1 billion integrals in my life, and I've just always done this instead. I've always stayed in my original setting of x, and I've always converted back into x after I'm done with my integration. Not because it's better. That's because it's what I chose. I know plenty of students who always convert their bounds of integration and always do what you see on the right side here. Nothing wrong with that at all. You choose what makes most sense to you and stick with it. Be consistent for yourself. But be aware that you should expect to probably see both occur in the textbook. And evaluating this is actually really easy. When we plug in 1, since this is like a polynomial expression, these aren't whole number powers, this isn't a polynomial, but since these are power expressions, we just get to keep the coefficients. When we plug in 0, everything goes to 0. So all I'm going to get left from this thing is 2/5 plus 2/3, right, minus 0. And that's going to give me, what are we getting right here? This will be 6/15 plus 10/15. And so I guess I'm getting 16/15 is our final answer here. All right. So again, two different techniques as to how we can handle this, but I just want to say, right, the whole reason we're doing this is because when you are performing any change of variable, you need to stop and be much more careful with identifying what variable all of the values correspond to. And that particularly is associated with our bounds of integration. We will get several other substitution techniques this semester. We will get a trigonometric substitution. We'll also get a two variable substitution, a u and a v, rather than just a single variable substitution like we're doing now. And the same lesson is the same for all of those. Be careful with what variable you are associating with the values associated with your integral here. You need to track that. I definitely expect all of you to write things like x equals 1, x equals 2, u equals 0, u equals 1 on your evaluations indicating the variable. You should always be writing those, and it's because this is just a way that makes you not make a mistake. These are just super common dumb mistakes to make. Don't make them. Write more. Keep track of your variables. This is just good bookkeeping right here. And that's all the examples I have for you today. The last comment that I just want to say is just a little bit of reading. I'm not even going to bring this up in here since you guys are perfectly capable of reading and fully comprehending this stuff on your own right here. The last idea that's laid out in section 5.5 discusses the symmetry of some functions with integrals. It's a pretty easy idea, but it's also a very important idea. It will come up several other times this semester. It makes lots of great shorthands for things. I will be including problems where I'm going to be taking advantage of it. You should be doing the same thing. So make sure you read those last pages there. And I will, as my final thing, I'll say, they introduce this idea on page 419, but then on page 420, in the margin of the page, they show a graph of each of the two symmetries that they want you to be able to see. And I think that these ideas are by far most easily seen just with a good picture. So make sure that you just look at those pictures on page 420 and see the two symmetries that they are discussing so that you can get some easy answers. These symmetries are just trying to make your integrals easier. So this is a pretty easy idea, but it's important, so like don't skip it. So make sure that you've read that stuff in section 5.5, the last idea, the two types of symmetries that we experience with integrals there, important stuff. That's all I've got for you guys for today. Big week one here, big week one. But I think that's a good call on my part. I think the biggest disservice I could ever do for you guys is to make week one easy and let you believe that that will be a trend for this class. And so I am okay with the fact that there's a lot of content here in week one. I hope that you are all, in a sense, broken into the idea that this class will take both time and effort from you. So I hope this week was good. As it is with every week, come to office hours, ask me questions. Email me, ask me questions. Do your MyOpen Math questions. Send me your MyOpen Math questions all the time in there. I want to interact with you guys about these things. If there's key examples that you don't understand, I'm willing to make more videos, post those as well for other like small examples rather than doing like a broader lecture like this. If you guys just say like, oh, none of us understand number 62, I'll just make a video doing that one right there. I can get that stuff posted as well. So stay in communication with me. Ask me for help. Don't fall behind. I know it's week one right here, so but right away I know it's a risk. There's a lot of stuff that's going on here, so try and stay on top of it. I hope that week one is treating you well here, and I'll see you guys in the MyOpen Math, in the email, in the office hours. Have a good one, everybody.